you did was everybody has a sample. So how many samples are we dealing with here?
2, 3, 4, 5, 6, 7, 12.
So there's 12 samples. How many samples do we have really? 12 samples of M&Ms, 12 samples of Skittles.
24.
So we're dealing with 24 samples, but really, when we do the difference, how many samples do we end up with?
12.
12, because we're measuring, and that's what our one dot is. So we're going to hone in on that today. I want to label a couple things here. So how can we possibly talk about these things? Well, last time we talked about a sample population, a sample proportion and a population proportion. Check this out. Here's how we're going to notate this. You ready? Well, when we do Skittles minus M&Ms, here's what we're going to label this as. You ready? P hat subscript S. What do you think that means? For what?
Skittles.
Skittles. A sample proportion for Skittles. So how might we label the M&Ms one? P hat sub M. Because P hat sub M is the sample proportion for the M&Ms. The thing about sample proportions is we can take a difference of sample proportions. We just notate it. P hat sub S minus P hat sub M. That's what we did. So one dot represents the difference in proportions. So the difference in proportions of orange candies in one sample of Skittles and one sample of M and M's.
Is it wrong if you say of 2 simple random samples of Skittles and M&Ms?
Two random. You want to be very explicit.
Okay, so you should split it. So
You
it
should
doesn't-
split it, yes. You'd be very, very explicit in what you say. That's a good question. So we have a relatively small data set here, but what is approximately the shape?
Approximately oval.
It's approximately normal. Okay, so the shape is going to be approximately normal. So shape approximately normal. What is the center? What is the mean?
Like 20.
No.
Oh,
Point-
are you estimating?
Estimated.
Can't you do max minus min? divided by 2?
.05. Negative .05.
Or the middle of the. Never mind.
You're estimating it. So somehow you're estimating. What did you say?
The median is negative .8
No, it's negative 0.0.
or something like that. Yeah, that's what I said.
So maybe we say negative 0.05. Okay. What about a standard deviation? What do you think?
Oh, don't we have to do the formula? Well, I'd say. No, we don't need to do that.
About
We just need to do-
0.2.
Okay,
There's
we-
a proportion, so we don't have to do that.
Yeah, we don't have tons of data.
Yeah.
Okay, we don't have tons of data. It's a little bit hard to see in our data set. If we had a larger data set, we'd see kind of how it shakes out. So I'm not necessarily super concerned with estimating this here. But I do want to talk in general about what do we do with this data? Why in the world would we take this sample or a bunch of samples and then plot them on a line here? What are we trying to compare to? So a Google search reveals that 21.6% of Skittles are orange and 20% of M&Ms are orange. Describe the sampling distribution of the sample proportion of orange for Skittles, X, and the sampling distribution for the sample proportion of orange M&Ms, Y, for samples of size 50. So here's what we're going to do. This is a chart laid out here. So what is the shape of a distribution of Skittles going to look like? What is the shape of the M&M's gonna look like? All right. What's the mean of Skittles? The mean of M&M's. What's the standard deviation of Skittles? The standard deviation of M&M's. So what I would like to do is I want to talk about what we're going to do, and then I'm going to cut you loose to do it. How are you going to determine what the approximate shape of a distribution of Skittles or M&M's is going to look like?
Look at the well, you do the 10, like the little 10 rule.
Okay.
And then you can also look at the probability, because if it's closer to 0 or 1, it skews if it's not normal. That's what's said in the book.
Okay. No, I love that.
I
No,
learned
no, I
that.
love it. I love it. It's good. That's good.
That sounds
That's good. So let's go back to that 10 thing in quotes. Not yet. Let's go back to the 10 thing. What did we use that for last time? Flip back in your notes.
to make sure it's like you can use the proportion.
Oh, it's the large
Independent.
counts 10 thing. To
No,
Okay.
independent.
So the large counts, we use it for independence. Okay.
That's for
Normality is large counts. 10% rules for
Yeah.
mean and standard deviation.
yeah.
Yeah.
Very
Okay.
much additive.
So if we, because the question is, can we apply the large counts thing to assess normality to this situation? How? Okay, so think about that. That's what you're gonna do on the first one. Okay, let's drop down to the mean.
How?
Okay,
Like
that's what you're gonna figure out. Yeah, that's what you're gonna figure out at your table. We're just talking about how we do this. Okay, I don't want to cut you loose without giving you some framework. So then, what about the mean? What then do we do? So, what did we do last time?
Look, what?
What did we look at?
P hat equals P.
So p hat equals p. So what needed to be true for that to happen?
The 10%. The 10. Yeah.
Sample
The
is
10
less
thing.
than 10%.
The sample is less than 10. Yeah, 1/10 of the population.
Okay, and then how do we assess standard deviation?
The standard deviation P hat equals square root of P times 1 minus P over N.
That.
I did my homework
Alright.
last period.
Ready, set, go. Fill in this chart for M&M's and Skittles in your groups. Go.
Alright, Nikki.
Okay. Okay.
Let me. Okay. Mean is like the
GG.
same.
Let go. Let go. Let go.
Mean is just gonna be.
The parts in the lesson where people are kind of like, well, what are we doing? It feels like we're doing this the same as last time. It feels like, well, that's part of it. Like this is a review, right? And so this part is a review. The next part is the new stuff. What I'm going to tell you is we're in a section of the book for the rest of the year called inferential statistics. There's a bunch of formulas on your formula sheet about inferential statistics. We're going to look at those in just a minute. But the ability to use large counts to identify normality is huge. We want to do that. But the caveat is you have to do it. Right? So even if you know, oh, it's true, it works, you got to show it. So you got to show these, review. You got to show these two statements. Then you can say it's approximately normal.
1 minus
You
P.
can't just say this. You can't just say this. So if you show this and you don't say this, that you get into trouble. So you got to say this is true, so this is true. Well, that's really cool because then what we can say is, well, we've got these things going on, 10% condition, so that works. So my mean of my sample of Skittles matches the proposed proportion of my Skittles, so my population proportion. Leon asked a really good question. He's like, well, what are we actually plotting here? And the thing that you have to keep straight is there's a claim. And the claim is that 21.6% of all Skittles are orange. Do we know if that's true? It doesn't matter. That's the claim. Then we use our samples and we're trying to verify claims using samples. Does that make sense? So it's the claim versus the samples, what comes out. So then over here we pop over and they match as well. And then so we come down here to standard deviation. We do our 0.216 times 0.784. That's 1 minus our proportion. And we get this is over our sample size, so we get 0.0582. Over here, 0.20. This one's a little bit easier with our math here, over 50. And then 0.0565. Do you recall that these formulas are on your formula sheet? So kind of recall that in the back of your mind. So now what are we doing? This information here has to do with one of the samples, the other sample. Now we're going to combine them. Okay, we're going to combine them. So at the bottom, we want to describe the sampling distribution of the difference between the proportions of orange M&Ms and orange Skittles. Notice what they said here. This is X minus Y.
Oh, it's a leftover?
Yeah. It's from Sunday. It's better not cook.
Are you looking at my rice?
It's not a chunky.
Oh,
Your
yes,
rice
rice.
is hot.
I have to warm
All right.
Rice.
No, I have to warm it up. That's why it's chunky.
Chunky.
You brought rice.
Do you guys have access to your formula sheets? Can you pull them out for me? I want to show you something.
I sure can.
So if you have access, pull it out. Would love to walk through this with you. But on your formula sheet, we have a lot of formulas that are going to deal with inferential statistics and finding differences of proportions, things like that. So check this out. So here we go.
I'm not doing it. Mine's like in a different folder. My whole binder for it's out.
We're not here yet. We will be soon. So we're not doing confidence intervals quite yet. What we just did, right? Does this look familiar? A single
Yes.
sample? Okay? What we're doing is we're doing two samples, and in this case, we've got a sample of M&Ms and a sample of Skittles. So check this out. We're not down here to chi-square yet. But in our formula sheet, check this out. Difference of sample proportions, difference of sample means. So, difference of sample means, special case when they're actually equal. Difference of sample proportions here, special case when the proportions are equal. These are the formulas that we're going to be using. So I'm pointing them out to you so that you know that they are available to you. Let's do a little bit of math here.
If you were trying to copy them down, they're already gone.
Mr. Moser has you beat on how clean his board is.
Oh, I can't wait.
How clean it is?
His board is literally the cleanest whiteboard I've ever
Who's
seen in
this?
my
I
life.
know, he's
Mr. Moser. It
He's
might
got-
as well be brand new.
That's very
got
true.
Impeccable.
serious board cleaning
How fun
habits.
is that?
Like marks on your board from common
Here's what I'm proposing.
Did you see the letter I wrote for
Yeah.
Ari's DM?
Why did I think that said arrow?
So here's this is approximately normal. Here's why. It's approximately normal because these two things are true. So because we tested the conditions for both of the samples, and they were found to be normal, the difference is normal as well. The mean of the difference between proportions is equal to the difference. So in this case, so then the standard deviation, and remember this formula is on your sheet, but I'm going to write it down for you. This one's kind of, we're going to have to squeeze a little bit in here. So standard deviation of p hat 1 minus p hat 2 is equal to the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. In this case, equal to, so what I'm showing you here, here's your formula sheet, check this out. And this might be a nuance, but I put this note in my notes because I wanted to make sure you kind of see this. Check out what's going on here. So this is the chart from your formula sheet. And it says two different things here, right? So the note at the top of this says standard deviation. So difference of sample means difference of sample proportions. I want you to see what's going on here. When you look down here, where do we get this? Where does this formula come from? Like, what are these things here?
They're each of their own, yes.
They kind of look like the standard deviations except for one small difference. What's the difference? when we calculate the standard deviation, we use this part, and then what do we do to it?
Square
Square.
root.
We take the square root of it.
You have to do it.
Okay, so we take the square root of it. So if you just use those things, you're going to get the wrong answer. And so one of the things you have to consider is you can go back to the formula, and we're actually going to use this formula here because it's going to play on what we've already done because we know the standard deviations from the original samples. Okay, so what were our standard deviations from above? Check this out. So we have our standard deviations from above.
How do you live? Where do you live? You don't, what do you do?
We have our standard deviations from above. And an easier way to do this, instead of worrying about all this stuff, watch this. You can go,
I think it's silly. They should pick this class period earlier in the day.
I saw the next one and I was like,
They should
okay,
make
I'm
this
not gonna
class
read
earlier
that.
in the day. Yeah.
you guys with me?
Yes,
You with me?
I have that,
Fair
I
enough.
have that.
Okay. And so what you've got is, but I want you to notice the distinction, and I know none of you pulled out your formula sheets, but
I don't have
notice that distinction when you get there. So what do you get? You end up with 0.0812.
Yeah.
So just make sure as you're using those things that subtlety comes out and you observe your order of operations. All right, I want to do this next problem in a very specific way because I want to work with you on understanding. There was some confusion at the end of the period last time when I put up the Z formula score. Remember that, where we were talking about the Z formula score? I want to go back to that because there are times when they're going to give you data represented by Z scores, and so I really want to work on that in this way. So Mr. Wilcox and Ms. Gallus calculated a difference between proportions of 0.08 from their samples. Calculate the probability of getting this difference of proportions or higher.
This is just like the N one.
This is just like the N1. And what we know is our distribution of differences, our sampling distribution of differences, what shape does it have? So we can sketch it approximately normal, and we're going to label it approximately normal. And what is our mean and standard deviation? Well, we calculated those, 0.016, and our standard deviation was 0.0812. On the AP test, we want to be sure to draw this. We want to be sure to sketch labeling it normal, having shown the conditions, label it normal, use your mean and standard deviation, and we're going to sketch. Well, what they're saying is, what's in the middle here?
0.016.
0.016. And what they got was 0.08 or higher. So they got 0.08, but we're calculating that or higher. So we sketch.
I do.
To calculate this, you can use your calculator. You can use your CDF formula. We're going to do it using z-scores. So our z-score is equal to our score that we're looking at minus our mean over our standard deviation. Okay, over our standard deviation.
She said she's choosing to send mine later just because
Why'd you? Oh, I was.
Well, on my transcript, like for college.
you can do that.
Hey, help me out. Can we stay on task? We're almost done. And when we're done, I'll cut you loose. So let's stay
No
with.
way. Okay.
I'm not cutting you loose. I'm gonna let you do your
Are
homework.
we gonna eat? Okay, well that sounds good. I'll
Alright.
find
Okay.
M&Ms.
You gonna eat your M&Ms?
Oh, really? That's so exciting.
Wait, I have
So, you can have more minutes.
So what are you giving? You calculate this number here.
0.8 cross.
0.789.
What is it? 788.
Dude, I'm the associate.
Okay. I thought it was 78.
Yeah, I
You
have
know what?
0.788 as well. Somebody rounded.
Why was 6 scared?
So-
7, 8, 9.
Okay, so how do we use this? How do we use this z-score?
You
This
go to
data
your
back.
chart and you.
Okay, pull out your chart. I want to practice this. Pull out your chart. So you can use your book.
Classic.
Go to table A.
That just really popped out of my brain.
Get out your table A.
that. Formula
I have
sheets
this.
and a table.
I have that too, Anita, it's
I
crazy.
don't know if I
No,
have the
I don't have
facilities
mine
for this.
either.
So grab your table A.
Why do we do it this way? Can we
So
not use normal PDF?
if it's 0.7,
You can, we're reviewing the different methods.
that's really close to 0.7.
Sure.
No, the thing is, it's important because 0.788 is really close to 0.79. So when we find it, do we look at 0.79 or 0.78?
Well, they're
So
not
which one is it
0.78.
closer to?
0.79.
Okay, so if it's closer to 0.79, you want to use 0.79.
There is a 0.788 on here though.
Well, we calculated the z-score, right? So we're looking for what's within the table, right?
Right.
Wait.
So what'd you get at, what was your area at 0.789 or 7.79?
0.78524. Is that right?
Okay, so that correlates to a probability of 0.7852. What does that mean? This is why we're doing this. I want to review what these things actually mean.
That there's a probability of getting this difference in proportions or higher.
No, you have to do 1 minus.
Wait, is it like
One
Ah,
minus.
okay.
Ah.
That's why I wanted to review this. So your table A values represent area at or below.
I understand.
So this 0.7852 is actually this area here, 0.7852. So our answer would be 1 minus 0.7852, which would be equal to
0.2148.
0.2148. Okay, wanted to review that. All right, flip over, let's finish this up.
Wait, what did you say that number?
That's the probability.
Of getting
So there's a
that or
probability of getting 0.08, a difference in proportions of 0.08 or higher in two samples.
Look at this Skittle and how sad and broken it is. I'm gonna take a look at Australian wildfires.
Oh my god!
Wildfires. Oh, they're crazy.
Those are so bad right now.
Okay, help me out.
My family lives in Australia.
Here we go. So help me out. This is the piece you're going to want, right, for your review packets here. Sampling distribution. For p hat 1 minus p hat 2.
Is that an if after the normal?
If and only if.
How? Okay.
How does that do?
Is that an if with two F's or
Yes,
is that a
if and only if. That's from geometry.
Interesting. Oh, really? Which?
If and only if.
Wow.
good thing I did
So if and only if means both things must be true.
So basically they have to both be approximately.
Mm-hmm.
Are you
Look like this.
So so as we've recalled, the center of the difference. So the center of the distribution of the differences of proportions is going to be equal to the difference in the means, and then our variability. And this is going to be this is our formula from before. Big gigantic square roots. Big gigantic square root. Yes.
So by center, do you mean mean? Is center and mean the same thing?
For this one, yes. This, because we verified
Yeah, it's approximately.
normality.
Yes.
I memorized the formula. It's the little things in life.
New seating
Maybe
arrangement
an
next time.
honorary rat.
Okay.
Yes, you should join the rats.
This is
maybe.
the best.
Well,
I may talk a lot, but this is the
Yeah.
best I've ever taken notes.
I know we
So I
talk
just
a lot,
wanna say
but I
that.
feel like I understand
Yeah,
a little bit.
I'm getting
So don't get mixed up in the formulas too much, but understand that, when we're talking about assessing the normality, this sketch comes from these conditions here. So we assess the normality over here. It is normal, we're just labeling it. And we use these symbols to say, you find the mean using the means. You find the standard deviation by using the standard deviations. And then any z-score that we calculate, which is what we just did, and not to confuse, but this is the difference in means on top, so sample minus population. And then on the bottom goes that formula for standard deviation.
This may be dumb, but why is it always minus?
Because that's finding the difference in them. Remember, z-score measures how far something is compared to the mean,
Okay.
above or
like,
below.
Gotcha.
But like for the proportions themselves, like can't you have one that's like insert the difference, the combination of both?
Say that one more time.
Like you know how for like the mean where we had like it's like the first thing minus the second, like the first portion minus the second
Mhm.
portion. Are there gonna be ones where it's like find the combination and everything's the same? You just do plus. Do you know what I'm saying?
Like plus minus.
Instead of the
plus.
difference between portions, a combination of portions.
No, because what we're trying to assess is the difference in two things. Like, are they the same?
Okay.
And in asking the question, are they the same, is the difference zero? Is really what, like, a difference of zero would mean that they're the same. All right, what I would like for you to do is this last check understanding problem in your tables, and we're going to check back in. So while you're doing this, you can go ahead and eat your Skittles, M&Ms. Okay. Thanks for holding off on those. But we're going to work on these. We got colorful goldfish crackers. I didn't bring any of those. So if you're holding out for that, sorry. But go ahead and do the check your understanding with your groups, and then we'll check back in about 5 or 6 minutes.
Is the paper cup the random?
What do we say for y when we get it? Do we have
Oh, so this is it. So this is called the large count condition.
And that's when I.
So you just have to have the one.
Yeah, so this is your Y right here.
Okay. It's not great.
Hey, Madison just asked a great question. Leon asked this as well. The large count condition is your reason why. And you proved it there. You got to show those 4 things. You got to show they're all greater than 10. Now, as we move down, this is another case where we've got that same formula that we're working with. I feel like we're hitting it. We're hitting it a lot. That should show you that it's an important thing going on here. But we calculate and interpret the standard deviation. You should have come up with a standard deviation using your formula of 0.097. So standard deviation, p hat 1 minus p hat 2. Okay. So the probability that the difference in the sample proportions of red crackers is larger than 20%. So here's what we're going to do. Let's do our sketch. Tell me about my sketch. What goes in my parentheses next to my n? Is it normal?
Yes.
How do you know?
Large counts.
We use the large counts condition. And what goes in my parentheses here?
Negative.
Negative 0.1.
And then 0.09.
Wait,
Very good.
I'm so, wait. I have to think.
Let's calculate this using z-scores.
Yes. Wait, how did I?
Oh, I'm dumb.
Okay.
So my z-score,
That's really
and showing the formula here. This is kind of a, you got to show the formula. You got to show this is what I'm doing. So just like you have to label it if you use your formula or your calculator, use your calculator, you have to label it. You also need to say, hey, this is the formula that I'm using. So we say this is the formula that I'm using. And again, this is just me helping you review.
Wait, so we have to like on the exam we'd have to write that whole formula?
That's how you ensure it. You ensure it.
But like
Remember, these
there's-
formulas are readily available.
But there's like, but like, do you have to write it? Like, it
If
takes
you're
some
using it, you
time.
should. If you're using it, you should. So then, well, really, all this information comes from up here. So, 0.2, and then minus, and then over our standard deviation of 0.097, we get what do you think about this?
Yeah, it makes sense.
That makes
Because the proportions like they're gonna be really tiny.
What is it? What does 3 standard deviations mean? Think about that for just a second.
Like
If we get 3 standard deviations outside the mean, what does that mean?
2.35% ish.
It's a small percentage, right? And so then if I hopped over to my table A, what do you get?
0.998. Well,
0.998?
0.99, basically 1.
So we want this piece here. So if I got 0.998, it'd be 1 minus 0.998,
Wait. Oh, okay. Yeah.
right?
Yeah, I did it through the calculator. Is that okay?
Did you label everything?
Yeah.
As long as you label everything, it's okay. I'm just
I know
I'm just wanting to give you a more well-rounded view. There are some people that teach AP statistics that do not feel that the TI way to do it is sufficient for not AP work. Does that make sense? So understanding
yeah.
how this works is going to help you understand more
It
fully.
gave me it gave me 9.91 to 10 to the negative 4.
Okay, it's tiny, very small. Your table A is approximate because of
Yeah,
It's
'cause
it's
of
limitations.
0.09, you couldn't
So
really
it's
use it. So yours is probably
0.002.
more correct.
so hers is going to be more accurate, but this is kind of like to be able to
Correct.
do this
I don't
is
know how
is
fast
is
Oh,
huge.
this is more
So
easy.
this was yours?
Yes,
The answer 0.002?
it's yes.
Because you would just minus that?
Yeah.
Okay.
Okay, I want to do one more thing. We're actually going to cover 7.3 day 1, but we have hammered this so hard. We're going to skip the exploration and we're going to go straight to the notes page. And it's going to be a pretty large review. And I love where you guys are at, but I want to go through one and then go through the box and then the example.
Oh, that's from the Princess Bride. I
Yeah.
know because that guy's haircut looks like the Amish people that got pulled over for driving their carriage drunk. Did you see that headline?
No.
There were 4 of them and they all looked like real life Shrek characters.
What?
So funny.
It was
I
pretty
would love to
iconic.
do that. I
Andy
love
knows
Amish
what I'm
people.
talking about.
Well,
All right.
I wanna do that.
So let's talk about
Over men.
They had good facial structure. I don't know, sure. Yes.
what's the difference here. So I'm just going to write that and ask you, what is the difference between this and what we've been doing? What are we measuring in this one? What is X bar?
Sampling.
Sample mean. What have we been working with the last 2 days?
Not that.
And
population.
numbers.
Yeah.
So we've been working with populations, but specifically, have we been working with means?
Sure.
That is a different kind of.
The means of what?
The probability?
Populations, like we've been working with proportions, right?
Yeah.
The means of proportions. What we're dealing with now is data sets such as, what is the average height of the people in here? So look at how this would be different. Instead of giving you a bunch of Skittles and M&Ms, what we do is we take groups of 5 and we'd measure the average height of that group. And so your sampling distribution is going to be dots that represent the mean of a given statistic. So how do you know the difference? Well, do you measure height in percent? Not percentiles. Do you measure number of pairs of shoes in percents? No. The average number of pairs of shoes. So we're dealing with a different type of data here. We're dealing with data that has an x bar and mean. Well, watch this. The mean of x bar, does this look familiar?
Yeah. No. Yeah.
No. I've never seen that in my life. I just like saying it.
Yeah.
And so what I'm hoping that you see here is the data, type of data changed a little bit. We're not looking at necessarily a proportion, we're looking at a different type of measurement. But when we do that, all of our statistics are still related to our parameters of our given population. You're going to love this next statement. If the population is approximately normal when dealing with these sample means,
It just sounds so weird. It sounds like you've seen somebody.
Yeah, it sounds like there's someone in spirit.
so if the population is approximately normal, the sampling, does this sound familiar? So these two things go hand in hand. So the things that we're measuring, those population parameters, are two different things. One is a proportion based on a percent. One is going to be a mean, but they're related in similar ways. Well, not surprisingly, when I sketch my little normal curve here, what I'm going to have is, if this is my sampling distribution, of x bar, I'm going to label it normal with my mean of use of x bar, also my standard deviation based on my sample size. And watch this. Statistic minus parameter over standard deviation. Have you seen that before? That should look very familiar, right? It's my sample, so my sample mean, minus what the mean is, the true mean is, over the standard deviation. I'd like for you to try to check your understanding. Identify what your statistics and your parameters are. Use your formula that you've been working on to kind of assess this. And work in your groups. We're going to check in about 5 minutes. Okay? This problem is actually your best friend. Because here's what happened. You see this right here? Look at the prompt.
He said they use ha ha ha.
What is perhaps the most important part of this prompt here?
Approximately normal.
That's right. Check this out, right here. Look up here. Undivide your attention, right here. When they tell you that the population from which we are gathering samples is approximately normal, good. This is good. This is very good. And if they ask you, what is the reason why you can say that your sampling distribution is approximately normal, you must say the population is approximately normal. All right, so when they say this, so now the probability that a randomly chosen pregnant person, woman, has a pregnancy that lasts for more than 270 days, so we have normal here, 266 here, 16 is our standard deviation, and we want 270 or above. And so if we do the z-score way, z equals X minus over standard deviation. So we have 270 minus 266 over 16 gives us a z-score equal to 0.25, which correlates to, what did the z-score of 0.25 correlate to?
0.598.
0.598. But we don't want this part, right? We want the other part, so we're gonna do 1 minus 0.598. So you got 40.13%.
Oh, percent, yes. So we 1%.
You can express it as a percent or a decimal. So then we chose a simple random sample of 6 pregnant women. Let X bar equal the mean pregnancy length for the sample. What is the mean of the sampling distribution of X bar? This is where that critical piece of information up top comes in handy. If it's approximately normal, what we talked about in 7.1 was if something's approximately normal, then the statistic matches parameter. That's what we just expressed up top, right? So our X bar is equal to our mean, which is 266. And if that's true, the standard deviation, so what we need to do is verify the 10% condition. What is the 10% condition?
Sample is less than 1/10 of the whole.
And why does that matter?
Because if it's greater, then it takes on its own characteristics.
Correct. So
Whatever
6 is less than 1/10 of all pregnant women.
And that's given away by it being approximately normal, right? Like that's another way you can tell, because if it tells you, or no.
Well, we want to get into the habit of verifying the 10% condition because if our sample is, yeah, that's kind of true. I see what you're saying.
Like if it's cutting it close, if it's not something as obvious as that and it tells you it's approximately
get
normal, can you generally be like, oh, it's probably less than that?
It would depend on the sample. Like, let's say you got a big enough sample that you only had half of your distribution, though, that would be way skewed, right?
I don't understand how you use the
That makes
approximate normals to figure out if the sample is less than 10.
Because there was it's like,
They're not, they generally don't try to trap you like that, but they want to know that you understand that you've got to have a small sample size in this case so that it doesn't take on characteristics.
isn't the book was also talking about skewing and how like if a certain probability is like closer
Yeah,
to one
closer
than
to
others.
this,
So
maybe
if it
more
doesn't
one.
meet the 10% and then later the larger rule, so then you could be like connecting to try to justify it.
Yes.
It doesn't really work well, but like it kind of works.
We're just scratching it. We're just at the beginning of this. So we're gonna get there. Okay? But be that as it may, we verify our 10% condition. So then our standard deviation of X bar is equal to our population standard deviation over the square root of our sample, and that gives us 6.532 days. Well, what does that change? In question number 4, the problem is, it seems like they're asking a similar question to up here, but what are they really asking about?
In the sample.
The sample. They're asking in the sample, not in the population. They're asking in the sample. So how does that change how we calculate this probability? Number 4, find the probability that a mean pregnancy length for women in the sample exceeds 270 days. Well, to calculate probability, we're using z-score. Well, our z-score uses standard deviation, and because our sample size is what it is, that affects it, right?
Yes.
So, stay with me. Is it still normal?
Yeah.
What's its mean?
266.
What's the standard deviation?
6.53.
Okay, so then our z-score would be
266.
270 minus 266 over 6.53, which yields a z-score of 0.612, which makes our percentage what?
27.
27.1.
About 27.03%.
That makes sense because
How
the
did I
further
get-
standard deviations away,
I
the
got the
less
same
there
thing.
is.
Yes.
I had to explain it to myself because I didn't think that was
How does that correlate
What'd you
to the mean pregnancy length?
How'd you calculate that?
I got 27.1.
She got the same.
Yeah, 0.271. If you make it a percent, you need the decimal too. It's just because we didn't use a calculator.
Yes, this would be a calculated value.
Yeah.
Okay. So, I am very pleased. I'm very pleased.
Good job, rats. We're getting that bread.